Well, if we already know a solution to a differential equation, can we find a second linearly independent solution using the first one?
I really don't know.
Well, let's see if we can. So let's assume we know a solution y1, and recall a linearly independent solution will be such that our second solution y2 cannot be a constant multiple of y1, because otherwise the Wronskian would be 0. Therefore, we assume that y2 is some function u of x times y1, because, that just might work.
Mercy.
So let's see. And u of x is not a constant. It's a little like variation of parameters from Unit 1 Lesson 7, and here is a procedure that should work in the general case. So what we do, we take a generalized second-order linear differential equation, and with division, whatever the second derivative is multiplied by, we can divide by that, so it is of the form where the second derivative appears with a coefficient of 1. So we got y double prime plus p of x times y prime plus q of x times y equals 0, and that's our differential equation, and we know that y1 is a solution. So we're going to define y equals u of x times our y1. And notice that the first and second derivatives, well, the derivative of this is first d second, that's u prime times y1 prime, plus second d first, which is y1 times u1 prime x. And then to find the second derivative, of course, that's the derivative of the first derivative, so that would be first d second, so ux times y1 double prime, plus second d first, so that's y1 prime u1 prime, or sorry, u prime, plus first d second, and that's y1 times u double prime, plus second d first, which is u1 prime times y1 prime. Notice that that term appears twice, so I could simplify it by saying u1 y1 double prime plus twice u1 prime, or sorry, u prime y1 prime, and then 1 times y1 times u double prime. So now that we have second derivative and a first derivative, we substitute back into our original equation, that's this one, and how I typed it, I just copied this and pasted this value for y, this value right here I put in for y double prime, and this value right in here I put in for y prime, and this is what I came up with. So here's the y double prime, here's p of x times y prime, and here's q of x times y. Remember, we said y, our second solution is u of x times y1. So now, messing around with this a little bit, factor out, see there's a u of x here, and here, and here. So let's factor the u of x out of those terms. We get y1 double prime plus p of x times y1. That should be y1 prime. My error. Maybe that's why I made that error. There we go. Plus q of x times y1. So sorry for making that error.
That's okay. That's okay.
Oh, great. Okay. It was just a typo. And anyway, then factor out the terms that have u prime of x. That's this one, 2 y1 prime. This one, p of x times y1. And that's it. And then the term, only one term has u double prime, and that's this one. And here's that. And you're wondering, why did I bother to do that, right? You might be wondering about that. But I want you to look inside the parentheses where u of x is the multiplier.
I think I'm perfect.
Okay, yes. What's in the parentheses here is our original equation, which we know is equal to 0. All right, because we know y1 is a solution. So that means this whole part of this thing right here is gone. So then what we wind up with is just u1 prime. Actually, what's left over is this part. Whoops, sorry. This part equal to 0. And that's what I've written here. Now, notice when I do this, if I let w of x equal u prime, then replacing this with w of x and this one with w prime, then we're down to a first order equation. And better yet, it's very close to being separable. As a matter of fact, it is separable.
I sincerely hope so.
Okay, so now we integrate both sides, and integrating this, of course, we just get ln of w of x, absolute value of w of x. This one, we get twice the ln of absolute value of y1, and integrating this side, we just get whatever the integral of negative p of x dx is plus c. And now to make both sides exponents for e, so you make this side an exponent for e, that turns out pretty nice, because this is really ln of y1 squared, so we wind up e to the ln of something is the something, so we wind up with absolute value w of x times y1 squared. And on the other side, we get e to the integral negative p of x dx plus c, which winds up being a constant. This e to the c will be that constant times e to the, whoops, negative p of x dx. Okay, now this can be solved for w of x by dividing. Just divide both sides by y1 squared. So w of x is 1 over y1 squared times c1, which is actually just an arbitrary constant, times e to the negative p of x dx. But recall that u prime was our w of x. That's how we started out this thing. That's why we made it a first order. We said let w of x be u prime of x.
Oh, I see.
Okay, and now if we wanted u of x, then we just integrate this whole big mess. So u of x is, of course, the constant c1, factors out, integral of 1 over y1 squared times e to the negative p of x dx plus some other arbitrary constant. Now, the values of the constant will not affect the linearly independent solution. It would just make a multiple of the Wronskian, so just let c1 equals 1, c2 equals 0 to keep it simple. So we do get our solution. y2 is u of x times y1, and here it is, y1 times this god-awful mess that we got when we did this. And that is how it works.
Ooh, that's hard.
Well, it's a little challenging, yes. An example might make this look easier. So, what do you think? We try to do an example?
I've had it up to here.
Well, check the example out first. It might not be as bad as you think. So let's solve the equation y double prime minus 9y equals 0, given that we know y1 equals cosh of 3x is a solution. So we're going to find a second linearly independent solution. Hence, we'll be finding a fundamental set. Okay, so our y2, just from this formula right here, is going to be y1, that's cosh of 3x, times e to the, remember that the y prime coefficient here is 0, so e to the 0 dx, well, e to the 0, integrate 0, you still get 0, e to the 0 is 1. So we get 1 over cosh of 3x squared. This is how I have to notate that. I would have called it cosh squared of 3x, but that's a little limitation to my software. But 1 over cosh squared is hyperbolic secant squared. So we got cosh of 3x times integral of hyperbolic secant of 3x squared, and now you probably see, well, isn't that just the derivative of hyperbolic tangent? And the answer is, sure it is. So we wind up with hyperbolic secant, or hyperbolic cosine, cosh of 3x times integrating this 1/3 hyperbolic tangent of 3x. And so when you multiply this by this, of course, tangent is sine over cosine, sinh over cosh, and that means the cosh would cancel. We'd have 1/3 sinh of 3x, but the 1/3 is irrelevant to whether or not it's linearly independent, so we'll just say our other independent solution is y2 equals sinh of 3x. Now I could go to the time and trouble to verify that the Wronskian is non-zero, but let's not say we did. Anyway, once we've gotten that, you've got your general solution is C1 times cosh of 3x plus C2 times sinh of 3x.